Sudarshan, why the class strength is too low? Sudarshan is there in the class, first of all. Fine. So yesterday we were looking at different types of rebar that we use in practice, right? So lastly we were looking at the TMT rebar, right? So can anyone tell how TMT rebars were processed to get the desired property? How do you obtain TMT rebar?
Done by the quenching process.
Yeah. So what is happening during quenching? So it is not
Uh,
only quenching, like quenching and self-tempering. So what is the whole process? So you're basically increasing the temperature significantly, and then the high temperature you are quenching your rebar in water, and then you are allowing it to cool. So right. So can you please explain that? So what happens during quenching process?
so outer layer will be formed in a different material kind of thing, and inside also the core will change.
Yeah. So how, what is the change? How it is getting changed on the outer
The name,
side?
I think I don't remember the name of.
That's fine, but yeah. So can you say, tell in terms of like, even if you don't remember the name, that's fine. How it is going to get modified? Is it going to get hard or soft?
Outer surface becomes harder while the core remains soft.
So the core remains soft, the outer surface gets hardened, so that becomes responsible for the strength of your rebar. And then, since the core remains soft, that becomes responsible for ductility of your rebar, right? Yeah, good, fine. So we'll just get into that thing. So the outer surface here that gets hardened. So initially you have surface, both surface and core as acetine, and then while you quench it, during the quenching process, the outer surface gets modified as martensite, and then your core remains as astenate. And after this you will be allowing it to cool. So during the time there will be a significant difference in the temperature variation between your inner and outer surface. So now the surface will be quenched, and then the inner portion remains at a high temperature as shown here. So the temperature tends to diffuse to the outer surface, so the outer surface gets tempered, and that becomes tempered martensite, and while your inner surface remains austenite. And then this is happening during the tempering bed, and then it will be sent to cooling bed. While it gets cooled, your inner surface, so that the inner region, so that becomes as ferrite and perlite, which is a soft portion of your rebar. So the inner portion contributes to the ductility, that is your ferrite and perlite portion contributes to the ductility, and the tempered martensite portion contributes to your strength. So for obtaining a good quality TMT rebar, you should have these two phases. Then only you can achieve both strength and ductility. To have these phases, it is very important that these phases are in its uniform shape. You can see the outer portion is in the form of ring. That is why it is called as TM ring bar. So the outer portion is in the form of ring, and then you have your inner circular portion. So this geometrical thing is very important to look at the quality of your TM ring bar. And then we looked at the advantages of TM ring bar. Right. So now to identify or select the TMT ring bars, what are the geometrical conditions that you have to look? So you know there are two phases. One is the outer strong tempered martensite phase, that is TM phase, and another one is inner soft ferrite perlite phase, softer core, which is in to select it, if the hardened periphery and the softer core are uniform and concentric, so that is this ring should be uniform in shape, and the inner portion should be concentric in nature, right? So how much this outer ring can be? So can it be fully something like this, and you will have some small inner portion, or you have, you know, such large inner portion in geometry? So this basically represents your core region, and then you have your core region. So can it be something like this? No. So to have this criteria, the co has specified that ideally you should have about 20 to 30% of the bar cross sectional area should be like a hardened periphery. So that should be your periphery, that is your TM face, and the core region should be more than 50%. Not ideal if more greater than 50% of bar cross sectional area is hardened periphery. So that is in this case. So consider the PM phases, that is sorry TM phase, that is the tempered martensite phase, is greater than 50% as indicated here. So this represents poor quality of rebar. So what happens when you have such a high hardened periphery? You may have a good strength, but the ductility get reduced in this case. Ductility gets reduced, whereas when you have less outer periphery, your strength will get reduced. That is why you should have balanced optimum amount of our hardened periphery and then the core level. So to have that, the condition is that the ideal case for good quality of TMT or QST bars, you should have the bar cross sectional area which contains 20 to 30% of your hardened periphery. And if your hardened periphery is greater than 50% of cross-sectional area, then that reduces this ductility significantly, and that rebar should not be considered. So to have meet this to get this criteria, we do TM ring test. So the test called TM ring would be helpful for us to determine the thickness of these faces, or the percentage of distribution of these faces, which we can use to just determine whether the quality of bar is good or not. So here you can see a test setup that you can use for assessing the faces, the two faces that you can look at in TMT ring bar. So the TM ring test for quality assessment of TMT rebars. So what you have to do is, you have to from the rebar, you have to cut a cross section and you prepare a sample. So you keep the cross section inside a rubber mold, and then you can expose this to 5% nitrile solution and keep it for 5 minutes. So there is a etching process that reacts, and that shows this cross section clearly, right? So you have a test setup shown here, and this is how the test specimen will look like. So now once you prepare this test specimen, this test specimen will be kept here. So you can see the test specimen, which is shown in this left side. So the pink mold, and then inside you have your TM ring cross sectional specimen, and that you can keep under this setup. So to capture the faces, you should have a camera at the proper lighting. So you can keep two lights on the sides to provide sufficient lighting to capture the image. So now the specimen has kept in a nitrile solution, which kind of helps you to etch the steel surface. So it's a very simple test, which hardly takes 5 minutes. Once you prepare the specimen, you can cut the surface, and that can be exposed to nitrile solution to get etched. And once that got etched, you can clearly see the distinguishing between two regions. So the outer ring portion becomes darker, and then the inner region becomes lighter. So those distinctions in the color, the surface, that helps you to identify the faces. So here you can see the sample preparation. So you have good and poor quality rebar kept inside, and now you are pouring this nitrile solution. So the nitrile solution is going to etch the steel surface, and you can see the rebar gets the color of the surface gets started changing, right? So in the case of poor quality rebar, the outer ring is not uniform and it is not concentric. Whereas if you look at the good quality rebar, the ring has formed nicely, and you can see a concentric soft center portion, right? So there are other images which indicates the difference between the cross sections for good and poor rebars. So here in this A, where you have nice outer ring formations with concentric inner soft ferrite pearlite face, indicates the good quality TMT rebar. And whereas when you have poor quality rebar, these are some indications where you do not have a proper outer ring formation, and in this case the thickness is too small in this region compared to other part of your rebar. Whereas here you can't see the outer face at all at these dotted lines. So here in this case, see, you can see in these portions there is no outer hardened periphery. And there are another the D also. So we can see there is no outer ring formed on the surface. So this indicates that the quality of quenching and the tempering process during the manufacturing thing. So if that control is not there during manufacturing process, that may lead to such poor formation of your outer and inner region. So better quality control of TMT steel rebar is essential. So that helps us like through regulations, and by creating more awareness how you should use or how you should test TMT ring bar for meeting the required performance. So though these rebars are named as TMT ring bars to provide better ductility and strength, since there is no proper outer hardened periphery and irregular like uniform, it is like irregular shape of your outer and inside region, that leads to inadequate performance. You may not have a good required strength or especially the ductility. So we use TMT ring bar to have good ductility, right? So in that case, you will not meet the requirement for the applications. So it is very important to choose the rebars which has good outer ring formed with concentric inner ferrite pearlite face. So these are other examples where you can see the deformations or discontinuities in the outer ring part. And this basically represents the rebars from different manufacturers. You know that we have plenty of manufacturers who produce such TMT ring bars. We have Tata Steels, Ice Steel, JSW, and anything else that you know to add on? So you would see a lot of
Vizag Steel.
what?
Vizag
Vizag,
Steel.
Isaac Steel. Okay, then so you see a lot of ads, right? So which ensures that if you use this rebar, your building will stay for 100 plus years. So those are like commercial lights. But in fact, if the quality doesn't meet, then those things will not stand for that long period, right? So anything to add on? Okay. So when you come for the next class, you just collect the details of different manufacturers that produce TMT ring bar, other than what I have mentioned in this class now. So you can add, there are, I have missed a lot that I don't want to disclose it here. So you can search and tell in the next class. Fine. So when we do, this test was conducted for different types of rebars produced from different manufacturers, and that indicates that the quality in certain and manufacturers are not up to the mark. So this A type of bars is unfortunately from outside India, and all this B, C, D, E, it indicates the rebars that we produce inside, like we produce in India. So this A type of rebar are basically the rebars from German, based on German manufacturer, and this B, C, D, E or the rebars from Indian manufacturer. So here one thing that to note is that this B, so that has a good TM ring combination, TM ring formation when you have larger diameter. But for smaller diameter, the quality is compromised, and not have a clear outer ring formation for smaller dia rebar, and this is the case for all the manufacturers. You can see like in C, D, E. So whereas as the diameter increases, they have some better control on the outer ring formation, and you can see in 16 for manufacturer B, it shows better quality rebar, and C also gives you better outer ring rebar, whereas all these things that indicates the poor quality rebar. And here also, some amount of extra projections, you can see it is not so uniform. And yeah, this could be due to the fact that rebar rips that is coming on, passing on your rebar surface. So how the next question is, how does it affect the performance, especially when we bend the rebars to use as stirrups? So when you do not have a proper cross section, that is going to crack when it is getting bent. So the poor TM ring can cause surface cracking. So here, this is example of TM ring bar which got and when you have good outer ring formation, you will not see any cracking while you bend the rebar. Whereas when you have some deformations on the surface, when the outer ring is not formed properly and where there is a discontinuity in the surface, so in that case, when you bend, you will start observing such kind of shear cracking. Why? Because this portion is not strong. You do not have hardened region here which can withstand the load while you bend the rebar. So that is why you observe a lot of cracking on the surface when you do not have proper ring formation, like in this case. So this will lead to affect the performance significantly when it is being used in the construction. So here you can see how those things will be used in constructions, especially for shear stirrups. We bend the rebar at an angle of about 135 degree. So when we bend, we observe such, if the quality of rebar is not good, we observe such type of cracking. So when we have such cracking, it is going to affect the strength and ductility of your material, and this also leads to potential variation in your system, which could cause corrosion. So the surface crack resistance should be checked if you are using the TM ring bar for meeting this application as shear stirrups, right? Especially this is very critical when you are constructing your structure in earthquake prone regions. So in such cases, you have to do check and ensure that your rebar can provide expected ductility for that particular condition. So IS 1608 has specified a test method to follow and check whether your rebar is passing the test method or not. So there is a test called bend test. So the specimen is considered to pass the test if there is no crack or rupture when you bend at 135 degree, 135-degree angle, right? So from the table, the mandrel diameter for bend test is given. So you can see the test arrangements here. So you have, you can keep your rebar and you can bend to 135-degree angle. So the nominal size of the rebar is given here. And then for that, the mandrel diameter for different grades should be considered. So that is this one to bend the rebar. So the idea here is that you are going to bend the rebar at a 135-degree angle and you check whether the rebar is cracking or rupturing. If there is no crack, your rebar passes the test. That's it. So that's all about the TM ring thing. So you have two faces: outside hardened surface, which is tempered martensite, and inside the core region is your ferrite perlite part, which is responsible for the ductility of your TM ring bar. And we can check the quality of TM ring bar is on TM ring test. So the TM ring test basically tells you the cross-sectional phase distribution. So you can identify the outer ring formation and concentric inner region and see whether that is adequate enough or not. If not, that indicates that you are using poor quality rebar. And then in addition to that, you can do bend test. You can keep your rebar and bend at 135-degree angle and see, are you observing any crack on the surface. If there is a crack, that indicates you're using a poor quality rebar and you can discard the batch. So the next type of rebar is that corrosion resistant steel reinforcement. So here, basically you are changing a composition of steel. So the bars with small quantities of copper and chromium and higher than usual percentage of phosphorus. This is called your, so this is what your compositions are for corrosion resistant steel. So you can see the ingredient amount of other elements: carbon, manganese, sulfur, phosphorus, silica, and corrosion resistance elements that you can add on. So now once you do all these changes to enhance the performance, you can do testing for check how good it is to resist the corrosion by obtaining the chloride threshold value. So test the chloride threshold of Shear corrosion resistant steel cementitious systems and ensure that the desired service life can be achieved. So these will be done as a quality check to ensure the user that you are using a right type of material to meet the desired service life of the structure. So the next type is the stainless steel. So in stainless steel, you will be having chromium on range of high chromium and nickel content. So this basically provides passive film on the surface, mainly chromium oxide. So that is very stable, and that helps you to prolong the corrosion initiation. So when your steel, which has more than 11% of chromium plus nickel plus molybdenum, this enhances the resistance to corrosion. So here you can see a picture which clearly gives you an idea how useful when you use this stainless steel in this environment. So here, there are a lot of piers, the columns that is used for constructing the bridge, that got damaged due to corrosion. So this is in the seashore level. So later, so these are like corroded piers with black steel rebars. So built 30 years later than those on the right side. Whereas here, in this case, you have pristine bars with stainless steel used. So basically, this structure was constructed first, and then this structure was constructed after 30 years later than this. So here the point to note is that though this was constructed earlier, this is standing in a good condition compared to this, because you used stainless steel in this case. Here the normal steel rebar was used, which is not capable of withstanding this environment, so it started corroding. So that is why it is always advantageous to use stainless steel for such kind of applications. But the only constraint is that cost. So stainless steel cost would range about 6 to 7 times the regular steel rebars. So the point is that if you have enough money and if there is no budget constraint and you want to have a long service life with a minimal repair work, then you can go with the stainless steel, which is a good option, provided financial or the money is not a constraint for completing the project. So here is another example where you can see the stainless steel rebars are used for constructing highway bridges. So this one is in New Jersey and another one is in Toronto, Canada. It is not that since it is costly, we do not use this type of rebar for construction. It is depending on the type of importance of the structure. So if the structure gets repaired and the amount of cost that you are going to put in, and then the time for fixing the repair, and since if it is in the prime locations to connect the major places, then even 1 or 2 days, if it is not getting function, that is going to affect the economy a lot. So in such cases, people tend to spend a lot of money in the initial stage itself so that they can avoid such scenarios in the future. So if because there are places where people believe like even if you put huge amount in the initial stage, you can be relaxed at the later stage with minimal repair work, and this that will lead to less repair cost. Whereas on the other hand, people tend to think that you can reduce the cost involved in the constructions by doing all you know uh, unethical practices, but then later that could cause severe damages, and you tend to do frequent repair and tend to spend a lot of money than the initial cost. So there are two way of looking at it. So one, you can spend a lot of money at the initial stage itself so that you can avoid frequent repair. Another one is like you have to be prepared that when you do not use proper materials or when you do not follow good practices, then you end to have a lot of repair works in the future. So there is a trend in some places to use the combination of both stainless and other steel bars in the same structural element. Okay, so in such cases, you have to be very careful for the galvanic corrosion. So the possibility of galvanic corrosion and its effect on service life must be checked before using such combination. What is galvanic corrosion? Please make a note of it and look what is galvanic corrosion. And so when we start the next class, I'll just briefly tell you what is galvanic corrosion and its significance on the performance. So have you heard this word galvanic corrosion before?
Due to
Yes.
salt,
Sorry? Sorry? Due to salt?
salt water, something like that.
Salt water. No?
Ma'am, some kind of corrosion between two metals when it is under some medium.
Yeah, right. So when you have two different types of metal, right, where when you have two different types of metal, you have different composition, right? So that is going to have a difference in its energy and potential, right? So there are based on its potential, there are list of materials that is listed out as galvanically active and passive metals. So the stainless steel comes under like less reactant, so passive metal. And when you have like a normal regular steel, that is like more reactive, that has more potential, and that becomes like active compared to your stainless steel. So when you have such two different metal elements in the same environment, then one is going to act as cathode, another one is going to act as anode, and that is going to accelerate the reaction. So the corrosion process will get accelerated when you have two dissimilar metals. And this has its own advantages and disadvantages. So we can use this concept when we need to protect the steel which is expected to corrode. So how can we do that? We use some unwanted metal which has high potential compared to your steel. So when you keep that unwanted metal, which is in high potential next to your steel, in that case your steel becomes cathode and the other material becomes anode, and that will start corrode. So you can protect your steel. So this kind of things you can look at when we study the repair strategies. So where we talk about sacrificial anode system to protect the steel rebar. So that's what the galvanic corrosion is. When you have two dissimilar material, then one tends to corrode depending on its potential level. So another one is pre-stressing steel strands. When we need to have high strength, we use pre-stressing steel strand. So can anyone tell how much could be the strength of pre-stressing steel strands compared to the conventional rebars? So in terms of yield strength or ultimate strength, however it is. So to compare with MS, that is 250 PM ring, it is 415 or 500 or 600. So what would be the range of this value for PS strands?
700.
700. No. Any other guesses?
5 to 6 times of this.
5 to 6 times of this. What? How much that could be?
Approximately 1,200.
1000 or 1500 approximately.
Yeah, so approximately you can say would range 1500 to 1800. So generally you can say it is like 5 to 6 times of your conventional strength steel rebars. So typically this comes in different sizes, So initially these type of 3-wire strands, so those are commonly used in railway sleeper applications, and the rest of the 7-wire strands. So you have 6 outer rings and one center one center wire called a king wire, and those are typically used for pre-tension and post-tension constructions, either in the form of bridges or high-rise buildings. So you can see the application of bridges, and it can be used as used in high-rise buildings as well. In some cases, it can be used simply as cables in transmission lines as shown here. So these typically comes in the form of sheathed strands, or it can be supplied in coils. Why? Because these are in general in high strength, and it is difficult to handle its side. So this comes in the coil, and it has a wobbling thing. So where as the length increases, you will tend to have wobbling effect as well. So to account all those things, it comes in the coil in coils in general, and it comes with protection system also. So the sheathed strands are commonly used in post tensioning applications to protect the strand from the corrosion. In some cases, you can even coat the strand, so using fusion bonded epoxy. So this indicates such type of coated rebars called fusion bonded epoxy coated strand. Again, when you look in detail, these high strength steel cables and strands can be used for huge infrastructure projects like in elevated highways, bridges over seawater, and power plants and metro rail projects. So this is your normal high strength rebar, right? So the strength will be significantly high, and the diameter can also be higher. And this basically represents your pre-stressing strands with 7 outer wires and 6 outer wires on a king wire. And this basically represents the group of strands as tender. And in general, to know about the composition of such high steel rebars in form of pre-stressing steel, you will have carbon content higher, and then these are like other important elements in the structure. So this contributes the high strength, and this also leads to the reduction in the ductility. So your pre-stressing steel or in general brittle compared to your TM ring bars, but it has high strength. So typically we keep our to keep our structure safe, we want the pre-stressing strands to be in its elastic stage, so that there will not be any permanent deformation which could lead to a brittle failure over the time. So these are obtained by a cold drawing process, and in the previous slide I have explained you what is cold drawing process and how that affects the or enhances the performance, especially the strength, by inducing residual stresses. So in pre-stressing strand also you will have some amount of residual stresses. So ultimate strength would range about 4 to 5 times than that of the typical conventional rebars. So after this processing, your structure will become like this, which has a matrix of ferrite with the plates of cementite. All right. So you don't need to look in detail about these microstructural thing, but the point is that to note, because of the cold weather, like cold drawing process, your structure gets changed, and that leads to some amount of residual stress to enhance the strength, and it reduces your ductility, so it becomes brittle. So since it has some amount of residual stresses, so so this becomes active, and this becomes sensitive to corrosion compared to normal conventional rebar. So I'll touch in detail about this in the next class. So how the corrosion would influence the performance of pre-stressing steel, and what are the precautions that we can take for such type of system or such type of rebars when we use in a concrete system. Right? So here you can see the same specimen. So from the same specimen, you have deformed bars and you have steel strands. So when you look closely, so this basically indicates from the same structure you have taken this deformed bars and steel strands. And in pre-stressing strand, you have to consider that these pre-stressing strands are already stressed to certain level. So typically 0.8 or 0.7 to 0.8 times your FPU. So the initial pre-stressing will be 0.2, 0.8 FPU. So this basically indicates that your strands are under stress before it is getting loaded. So these are all indication that your strand is under high energy state. So you have residual stresses plus this pre-stressing forces. So this tend to accelerate the corrosion process when it get chance to corrode. So the overstressing can decrease the corrosion resistance. So overstressing in the sense, when we again increase the initial pre-stressing beyond this level, then the corrosion resistance can be significantly reduced because that will be in higher energy state, so that tends to react faster. So the reduced number of corrosion cells can also lead to faster growth of existing corrosion pits. So here in this case, because of that such scenarios, you will you can start observing such kind of corrosion pit formation on the surface. So whereas for the normal deformed rebar, there will be pits for pit formation, but that will not be as significant as in this case. So here the corrosion cell can be less pre-stressing for pre-stressing strands, and that could lead to faster growth of the existing corrosion pits. So again, these are all on the same plane. So the at this particular cross section, if you look at, you have 7 wires. So again, this is going to run along the way in a helical shape. So this has a tendency to affect the adjacent wires as well as it corrodes, and that is going to particular breakage, or sorry, that is going to break this wire, and eventually the other wires will also get break, and which further reduces your strength of strand itself. So in that case, you will not be meeting the actual purpose of using the pre-stressing strand. So the purpose of using pre-stressing strand is to increase the strength, but when it starts corroding, the strength will be significantly decreased due to the breakage of the outer wires. All right. So that's it to summarize things and in detail about how the pre-stressing steel will corrode and what are the precautions that we can take to account, that will be covered in the next module. And then we will look in detail about the non-metallic rebars that we use, and then the coated rebars in the next class. The performance of coated rebars and non-metallic rebars. And for some of these materials are from literature, so you will not have a defined textbook for this. So I have uploaded the textbook that you can use for repair and strengthening thing. Okay, so that is by Peter Emanson. So that I have uploaded in the reference materials. And for getting the actual content for these thing, you can have to go through the reference of this. So this is basically literature paper. I think for this material part, the class materials itself, whatever the PPT that I shared, that it's good enough for your reference. And if you are interested to get more details, you can go through these references. It's all good. Okay, so can we meet on this Friday? Do we have holiday on that? Specify you know.
Friday is holiday.
Okay, then we'll meet on next Tuesday.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Ma'am, can you stop the recording?